Okay, last video. 2 questions, 20 minutes. This one we're going to do all 3 in 20 minutes. We shall try. Anyway, right, question 6. We have got a string A and B. A there and down here B. They're 4 meters apart. A small heavy ring is threaded onto a string, so it doesn't say how long this string is, but it's got to be longer than 4 meters, because as this is spinning around, it is on the same level as B. So you've got the string there, that is horizontal. A small heavy ring C, so I guess this is point C. I don't know how much it weighs, so let's write an mg there. Angle, we'll call that angle theta there, and that's 4, that's theta. The radius is 3, so of course we've got a very nice 3, 4, 5 triangle there, so that makes sine theta equals 3/5 and cos theta equals 4/5. Of course we've got string, so we've got a tension here, and the thing that you may not think about at first, of course we've got another tension there. So this is the same string. This is the same string. We've got a heavy ring, so of course the ring can move through as it wants. It's a smooth contact there, so there's no friction. So what that means is that it settles in this particular position, but crucially, that force there is T, that force there is T. It's the same tension in those 2 parts of the string. That, for the moment, though, doesn't matter. But as ever with a horizontal circle, so of course it's moving around like that, a conical pendulum, we have got in equilibrium, forces up equal forces down. Forces up, that is my angle, so of course I know that that angle is also theta, alternate angles. I have got the cosine component, so I've got T cos theta equaling mg. Cos theta I know is 4/5, so T times by 4/5 is mg, and it means that T is equal to 5 mg over 4. If I then look at what's going on in that direction, I'm using F equals ma, I'm resolving towards the centre of the circle. I've got all of that tension, plus I've also got this component of the second tension, that's the sine component, because it's opposite, that length there is the opposite length. So I've got T plus T sine theta is equal to, I've got to find the speed, so mv squared over r. T, which I know is 5 mg over 4, plus T, another 5 mg over 4, times by sine theta, which is 3/5. And that's equal to m times 5v squared over r, and of course the radius is that 3, that length is 3. The 5's cancel, so we're left with quite a nice 5 mg over 4 plus 3 mg over 4 is equal to mv squared over 3. I've got 8 mg over 4, which gives 2 mg, is equal to mv squared over 3. The m's cancel, so v squared is equal to 6 mg. And v is equal to the square root of 6r. That's the problem. I was pausing because I was worried that I still had an m. That m cancelled there. So v squared is just equal to 6g, and v is equal to the root of 6g, which is equal to the root of 58.8, which is 7.7 meters per second. Okay, lovely, excellent. That was speedy. Let's do question 7. Question 7, we have got a turntable. So it's going around like that. There's my turntable. We've got a penny. There's the penny. And that distance is 0.1. A second penny is placed on the turntable so that speed is half of that of the first penny. Okay, all right, so where do I put it? Will it go there or will it go there? And I'm sure that some of you will just, oh, well, it definitely goes there, and probably write down the answer to the first one anyway. I'll just put it there, you know, I'm not sure, and, you know, there's space there, so why not put it there? And I will call that distance A. Right, now because it's going on the same turntable, of course, we know that the angular speed is constant. Angular speed is constant, it's turning at the same rate. So if we look at the first penny, penny one, the radius for that is equal to 0.1 meters. Using V equals R omega, I know that V is equal to 0.1 omega. Omega is equal to 10V. For the second penny, the radius, well, I've called that A. I know that the velocity, or I want the velocity to be half of the speed of the first penny. So the first penny, I called that speed V, so let's call this a half V. So if I use V equals R omega, I'm going to get my velocity, a half V in this case, is equal to R, which is A times by omega. Omega, as we said, the angular speed is constant, so I'm going to pop 10V into there. So a half V is equal to A times by 10V. The V's cancel, and I know that a half is equal to 10A. A is equal to 1/20th, which is 0.05. And this, you know, as I said, that some of you could have probably realised this from the start, it means that my kind of original placing of that isn't actually correct. So if that's the first one that's 0.1, this second one is actually kind of closer, it's half the distance. And of course it's half the distance, because if it's travelling at half the speed, it's got to be going, you know, half the distance, hasn't it? Going around here, it's covering less distance, so it's going to be going less speed. If it was around there, it would of course be going at a faster speed because it's travelling more distance in that time. Same angular velocity, but you've got this differing speeds. Okay, once we've done that, we can look at the second part. The first penny starts to slide when the angular speed reaches 5 radians per second. So if I just focus on this first one, so I'm just drawing this first one, mg, that's the centre of the circle, and the distance is 0.1 metres. It's accelerating here. And at first it appears that there isn't actually kind of any force there acting in this direction. Of course there has to be. We can't have any acceleration if there's not a force. And of course the force that's present is the friction. So the friction always opposes the motion. Friction is going to be acting in this direction here, because of course you can imagine it's going to spin quicker and quicker and quicker, and if at some point, of course, it doesn't slip towards the centre, it slips away from the centre. Friction opposes the motion. It's going to want to slip out in that direction, so friction is going to be acting in that direction there. No other force is acting, however. So I'm going to use F equals ma. F, resultant force, is in the direction of motion, but actually the only force is friction, and that is equal to ma. Angular speed, because we've been told the angular speed is equal to 5. So the friction is equal to M times by 25, the angular speed is 5, times by R, which is equal to 0.1. So F is equal to 2.5 M. M, of course, being the mass, the unit is Newton. So note, this is different to the normal reaction questions. Things slip if there's a contact force, because that R is equal to 0. However, here the thing is slipping because the force given by that particular angular speed is bigger than the friction kind of available for these two contacts, so for the surface and the penny on the surface. So we can now look at the force on the second penny. It is the same coin, so it's going to have the same maximum value of friction, same friction of 2.5 M. It's going to have the same mass, it's the same coin, but it does have a different radius. So that radius is 0.05, still mg. So we're going to use F equals ma. My frictional force, 2.5 m, is equal to m multiplied by omega squared r. The r is 0.05 m. 2.5 m is equal to m multiplied by omega squared multiplied by 0.05 m. Now I've got too many m's there. Have I got too many m's? That m is a unit. That's a metre. That's a bit dangerous, isn't it? Okay, so now that looks good. Those m's cancel, and so I know that omega squared is 2.5 over 0.05. Omega squared is 50. Omega is equal to 7.07 radians per second. Okay. Number 8. Let's attempt number 8. It's a starred question, but again, there's nothing particularly tricky about this. 2 kilogram mass comes down like that. We are travelling in a vertical circle, so we're going to be looking at energies first. Just looking a little bit ahead, it looks nice. We've got lots of numbers as opposed to algebra. A breaking strain of 50 newtons. So when we get to a certain tension, that's when we need to find the angle. So quite commonly you get questions where the tension in string is 0, string becomes slack. So this is actually giving a specific value when it breaks. So let's look at this diagram. So here's the bit of the circle coming round. I know that's equal to 2g. I've got this value of theta. B, is that where it starts? Yep, it's released from rest at point B. C is here. It's I'm going to call B the 0 level, I think. So I am going to end up with negative heights, but that's fine. We can manage with that. Height is equal to 0. So my energies, GPE plus KE is equal to 2G mg times by h, which is 0, plus a half m times by 0 squared. The velocity is 0. It's released from rest, so the initial energy is 0. At C, so this is C. H is that distance there. It's negative. I don't know this. Shall I call it A? Generally seems to call things A. So that is A. That is the sine component. So H is equal to A sine theta, but of course it's going down, so it's negative. It's below my 0 level. So I know that for C, the total energy is equal to m g times by h negative a sine theta plus a half mv squared. Equating those by the conservation of energy, I have got 0 is equal to negative, that negative there, 2ag sine theta plus a half mv squared. A half m, I know of course m is equal to 2, don't I? So that works out to be v squared. It looks very horrible, but that's v squared. Put that on that side, 2ag sine theta. Okay, so now I need to look at forces. Looking at forces, it's on a string, isn't it? It's on a string, so I haven't shown any forces there, but that's equal to, that's the tension. So what I've got, if I resolve towards the centre, I've got two forces. I've got T acting towards the centre. Of course, what I'm doing here is I'm looking at resultant force in the direction of motion. T acting towards centre, I've got a weight component acting away from the centre. This angle is a little bit awkward, isn't it? But if I've got theta there, I know that's 90 minus theta. This is 90 minus theta. So it means that that angle there is theta. Okay, let's draw that out here, shall we? So that's theta. This is 90 minus theta. Sorry, yeah, that's theta. This is 90 minus theta, which is equal and opposite to that. So this is 90 minus theta. That is 90. Oh, so this is theta. And this is my 2g. I want this component here. It is opposite that angle. So 2g sine theta. That is equal to ma. And ma v squared over r. R is a, meaning my radius, not of course that acceleration. Has that been confusing people throughout? Apologies if it has. T minus 2g sine theta is equal to m v squared 2ag sine theta over a. The a's cancel, so t is equal to 2mg sine theta. And I'm pausing, do I know m? Yes, I know m. M is equal to 2, so that's going to be 2 times by 2g sine theta plus 2g sine theta. Have I got too many 2's? Nope, that 2 is from the v squared and that new 2 is from the mass. So we've actually got 4g sine theta plus 2g sine theta, so 6g sine theta. So that is a general expression for the tension. We want to find the value of theta for a specific tension. So when T is equal to 50, 50 is equal to 6g sine theta. And of course, well, as long as 50 over 6g, yeah, that's less than 1, we're going to be able to work out our angle. That works out to be 0.850, so my angle is 58.2. So what do you think? Less than 20 minutes? 19 minutes, excellent.